Okay, so just like we were discussing last time, we didn't we almost finished a problem, but basically we started with a problem where we had a general cross section, we had a flange and a web, and this was subjected to some type of shear force. I don't know if you were going up or down, it doesn't matter, but basically here I think we call this, remember properly, A1, which would be the flange, and this over here, A2, which will be the web. Okay, so we were talking about how will be the distribution of the shear, and we probably did something like this. I'm guessing that was going from 0 at the top here to a value, and then it was a jump over here due to the thickness. All right, and then I say, okay, that's very good to look at the distribution, but really in this case what I wanted to see is how much of the shear force was on the flange and how much of the shear force is carried by the web. So we saw that the total shear force carried by the flange was equal to 3.82. Okay, and we knew here that V was equal to 12. So without going into too many details, all right, I don't want to continue too much this work. So what could we say about, so we could say that V equal to E that was going to be resisted by the, sorry, V no F by the flange plus V resisted by the web. So basically from here, we could say that the amount of shear resisted by the web will be V minus V flange, which is 12 minus 3.82, which will give you the amount of shear resisted by the web is 8.18 kilo. Okay, and again, I think you should have done some of this in soil mechanics, but here my goal of this is not that much about just this shear there, is to know what is the shear useful for, no? Because what did we discuss at the beginning of the semester? We discussed that without knowing, every time you are doing a derivation or we are doing a derivation, we make the assumption that the structure needs to be what? Long and slender, no? So if it's long and slender, what does that imply? What would be the main load on the structure? What would be the main deformation? Would be bending or torsion? Bending, no? Okay. And if thing breaks in something that is moving that is long and slender, it will break due to what? To bending or torsion or shear? It will break due to what? If you try to break something that is long and thin, how do you break it? Bend it multiple times. So what would be the critical load? Bending, no? So what would be the critical stresses? The stresses due to bending. All right. We say that the shear becomes critical when you have structures that are small and thick. Now, if you want to break it, what do you do generally? You try to twist it, no? Okay. So really, for long and slender structure, the most critical load should be bending moments to find direct stresses, not really that much shears. Okay. However, shears are very important in order to do what? So, for example, if you want to put on top of a beam, let's say some type of plate, okay, and you need to bolt it. So, how are you going to do the design of the diameter of the bolt that you need to put or rivets, let's say, and what should be the spacing? So, for example, if the plate, let's say you have a beam and you put on top of a plate, if they become apart, it would be due to what? It would be due to shear, no? Because two surfaces, remember, without shear is two surfaces in contact, no? All right. So basically, shear, what's important is for something that is called generally in the textbook, build up members. Okay. So I'm going to write here. So shear is not critical for failure of the main structure but it is extremely important for the design of what they call in some textbook built-up members. All right, so let's look at that. We're going to do this one example. I will do the same one. Let's see, it's the one up here. Then we can do a different one. I can come up with something different. Okay, so I might change a bit the example. So build-up members. So next section is going to be what happened here. Somebody is nothing with this, no? Yeah, but you had a whole week to do it. You're right. All right. No, I wasn't saying I wasn't talking about you. I was talking about the life. So don't worry about it. Okay. Yeah, no worries. Okay. Anyway, so build-up member. So what is a build-up member? So the example I was talking about, for example, is like, let's say you have and it doesn't matter what type of beam, but I always start to write this one because I think I-beams are the most used beams, no? When you were looking about the construction around here, everything was I-beams, no? If you look under the 18-wheelers, what do they have at the bottom? What is the bed? It's two I-beams, and they put on top a plate, no? Okay, so extremely widely used, and probably now you know why. I think we already discussed why is all the area at the top and the bottom. Why of this shape? That's what the bending stress are, no? Top and the bottom. Okay, do you remember? Here would be what? Shear, no? It's important here in the middle if they shear. But since those members generally would not break due to shear, you see that's what they call the least area, no? Okay. So anyway, so let's say you have this, and just like we're saying, you do the bed of a truck. Okay. We put another I-beam there. So let's say now you want to put on top of it. The same one. Oh, I put the same color. Okay. Let's say you want to put a plate. Okay. Okay, so for example, you will have probably to use bolts over here. Or rivets, whatever you want. So what should be the diameter of each one of the rivets or the bolts in order to resist the load, or how many of them will you need, no? For the plate to step on it and do not come off the structure when it's bending. Because when it's bending, what's going to happen with this in bending? This structure is going to deform now, this shape, and the top one, the same thing, no? Yeah. So between them, what will be the load? It will be shear, no? So the bolts over here will bring you to what? Shear, no? So that's when it's important, really, what is the shear over there? So we can do the design of the bolts and so on and so on. Okay, so the example I generally do in class, let's see if I have it somewhere over here. Yeah, is and we'll do it next if you want, but for example, let's say you needed to connect, let's say you want to build whatever, made out of wood, okay, if we think about wood. Let's say you want to build out of wood a T-section. All right, one I-beam if you want, but let's make it T-section. What is better? Maybe to take one piece and build it this way and just put one nail. Okay, and then put another nail over here, whatever you want, okay? Or is it better? What will be the other option? You can put One over here, you could put another one on the side, no? Okay, and then you will have more over here, whatever, and another one over here, and so on and so on. So this could be here called the S, where S, let's say, is called the spacing. Okay, so I'm going to put it here. Let's say structural engineers. Is it better with light or without light? With, okay. So structural engineers generally, I mean, do not use shear, but shear flows line connections between build-up members. So basically here, this is important. The shear, you will understand why now, will be equal to, let's see, the shear expression that we have times T. So let's put it here where, what was the expression we used for this was dq over IT, no? So here, what's important to recognize is that what will be the units of this? What will be the units for stress, the shear stress? Okay, Pascal. So what is 1 Pascal? Is Newton per meter square. So this will be what then? Newton per meter square, or will be pound per inch. But basically what we have is force over length. Okay, so basically this will give you the force that is done along the length here of the beam, no? So now you can define how many connections, rivets, bolts you need in order to resist that force per unit length. Okay? So I need to go to the next page. I'll probably do another figure. All right, let's do another figure here quick. I'll do an easy one for the spacing. Again, you could build this like having one nail over here. Then you could put another one here. Right, and let's call this here. We call it before the spacing. So this is S equals spacing. Okay, and let's say here we have the nail of the bolt here. Let's say nail or bolt. Okay, let's say the nail. Okay. So the nail The design we have, let's call this one, a certain shear force for which it will fail, no? Let's say V connection. So VC is the shear resistant load to failure of connector. So the connector here can be what? Can be a nail, can be a bolt, can be a weld, whatever you want, okay? Okay, so the definition here of the spacing is what is the resistance to the connector divided by the shear flow. And the way I remember this equation is not that I remember it, okay? It's because what should be the units? What should be the units of the shear force? Let's say it will be Newton. What are the units of the shear flow? Meters, so this and thus being length, no? Yeah. And here, let me see something. I think I'm forgetting something. Let's put here N. Okay. And N will be number of connectors. All right, so let's do one example. Okay, so I will use the same example. I think it's good. Once we don't have it, doesn't matter. Just for the values. There we go. Okay, so in here's the one I kind of mentioned before. That's really the one I do. So let's say we want to build an I member. On the first case, okay, the way we decide to build it, just by putting one nail over here. Okay, then you could put another one over here. Okay. So this is the spacing. And let's see what they give us. So here they tell us that the thickness of the flange is equal to the thickness of the flange is equal to 0.5 inches. Thickness of the web will be 1 inch. So 0.5 inch, 1 inch. So this is the flange. The web, and that distance over here let's just call it H, is 4 inches. And that here the base of the flange, to use the same notation we have been using so far, is 3 inches. The flange is half an inch. Okay. And then the other way we can build this will be, let's see, will be by doing just one bigger web. And then here we take 2 pieces on each side. You better figure than me. This is not symmetric. And then we decide basically to put here just one nail on this side, one nail on this side, one here, one nail here. Oh, I'm doing bottom, but and here we could do the same thing at the bottom. Okay, but I didn't put. Not that important. And basically the dimensions will be the same. Okay, so let's say this will be case A. And this would be over here. It's big. And here again another ball. One or nail. We're talking about, let's say it's wood, okay? Okay, so let's say here, given a spacing S equal to 9 inches, and we know that the maximum shear force that can be resisted by the nail is 40 pounds. So basically here we have our nail. This is our connector. We say it will break in shear. It can resist in shear a force of 40 pounds. Okay. So knowing that, determine the maximum shear force V that can be resisted by the cross section. Okay, so I don't want to do too much, and let me just do it maybe in this one. Let's say V will be this force over here, no? The shear force. Okay, so what is the first thing we need to do? Is what we did last time. We need to find, in order to find the shear flow, we need first to find what? The shear. Okay, so in order to find the shear, which is tau equal dq over it, all right, what do we need to do is to find I, no? Okay, let's go here. Okay, so this is probably similar a bit to the what you did today for the assignment. First thing you need to do is, this is our cross section. I'm going to start putting values because maybe now we can just do it. I can just do it. So we know this is the flange. This is H. This would be here the flange. And this will be T1. Okay, so because this is symmetric, we know right away what will be the neutral axis, no? Okay, we don't need to calculate the centroid. I think on the assignment you have for today, you needed first to calculate the centroid in order to know where the neutral axis was, no? And then you could calculate the moment of inertia. So in this case, we need to find here the moment of inertia. So there's multiple ways to do it, but the fastest way to do will be we're first going to do the whole thing, which would be what? 1/12 of F times what? 8 plus 2 BF cube, no? We can do the whole thing. And then what could we do? We could just calculate now the one and remove these two over here, no? Okay, there's multiple ways. You can take that one and move it to the middle plus do this one in the middle. No, there's more than one way to do it. And this one would be what? So let's see, minus, hopefully we have space to do it here, minus 2, because it will be the two red areas, the two on the side. So what is the base over here for this one? So it will be BF minus EW. But I'm doing twice, so it's BF minus TW divided by 2, no? On each side, no? So divided by 2. And then what would be the height? Oh, okay. So I'm going to put here 2 divided by 12, okay? Because it should be 112, no? Put it inside if you can of H cube. So basically what I'm trying to say is that this is here. This over here is those two areas over here, okay? And this term over here is the whole thing, is like if it was the whole thing. All right. Do you have any question about the way I did this? No? So I'll give you the value. If you do the calculation, this should give you 20.58 inch to the 4th. Okay, another thing, the other day somebody asked me or mentioned to me, how can I check what is the I, all those the cross-sectional properties? I'm pretty sure if you go to CATIA and plot it, it will give you all those properties, no? Yeah, okay. So if you want to check, all right, you can go and check. All right, so okay, so let's go here. So next, now the equation will be, the general equation we need to use is tau equal dq over IT. So over here, we need to find V, we know I, we know T. The problem here, generally, the most complicated term to obtain, or to obtain the appropriate one, is the first area moment of inertia Q. In order to help you, as a general rule, doesn't mean that it works all the time because it depends on design. Determine the Q of the I'm going to put area instead of member that you want to attach. So, saying that, okay, and here's a bit more. The first one is pretty easy, but the second one might be a bit complicated. So, in this case, what is the piece that you're trying to attach? You're trying to attach the, you could think that like the top piece to this one, no? Yes? Okay. So let's say for case A, so let's do case A, then we do case B. I'm not going to start the discussion. So for case A, what would be the problem? So we have again the structure way. I'm going to do here the neutral axis. So what is the piece we're trying to attach? This one over here. So let's try to calculate what will be the Q of this piece, no? Okay, so if you remember, what was the procedure to do this? So Q, let's say case A would be equal to what? Is generally the equation is YdA, but we say you could approach this by what? Area times distance from neutral axis to the CG of the area. So this will give you what? Q sub A would be equal to what? What will be the area? dF times dF. And what should be the distance to the CG? H, okay, it is, no, H over 2 will give you that distance here, no? Yeah, H over 2 plus TF over 2. Well, let's put some values because just want to double check with my notes over here. So this will give you what? So this will give you what? Is EF is 3. T flange, I think, was half an inch, no? If I remember right. Then H was 4. Was it 4? Yes, 2 plus half an inch. Divided by 2 plus 0.25. So if you do this calculation, this gives you what? Q sub A is equal to 3.375 cubic inch. Okay, and how many nails is holding this piece over here? 1, no? So let's say here for N equal 1 nail, okay? It's one number of connectors. So again, really, otherwise you could have done what? You could calculate this one and say that you have 2 nails, no? One on top, one on the bottom. But if you do just for the top, it would be the same thing on the bottom, no? Okay. Okay, so let's see. What are the equations that we have so far? We have derived. So let's say tau sub A to make the difference will be equal to V sub A, Q sub A over IT. That's one equation that we have. What is the other equation that I gave you here? Is that the spacing S equal to N P connector over Q. And what is the other equation that we have? Q sub A, or put here Q sub A for the first one, will be equal to what? BA will be equal to tau A times T. So this is, let's say, known equation. Okay. So depending on the problem you need to solve, you will find different values. Okay. I mean, different expressions. I don't want to make this a cooking formula like you need this recipe. I want you to understand what needs to be done. So basically, we have these equations. What do we need to calculate out of these equations? What is the variable that we need to determine? What is the question? Okay, the total shear force. So in this case will be, since we have two cases, we call V sub A for case A, V sub B for case B, no? So what we need to do is find V sub A, no? The maximum shear force, all right? So let's see how we can combine this one. So let's start by the last one. So Q sub A for case A equal to tau sub A times T. So this is equal to what? V sub A Q sub A divided by I times T times T. We have here Q sub A will be equal to VA Q sub A divided by I. But now from the second equation, what is Q sub A also equal to? Will be equal to what? From this one, I can find Q sub A will be equal to N, the number of connection, times the shear force at which the nail will fail, or the connector, divided by the spacing. Okay, so now if I take this part over here, I can solve for VA will be equal to what? N times VC times the area moment of inertia divided by Q sub A times the spacing. So do we know everything in this equation now? What is N? In this case, N will be 1. BC is 40. I was how much? 20.58. BC, Q sub A, so S, I think was 9, no? Yeah, 9. And Q sub A, we just calculated Q sub A. 3.375 cubic inch. So we do the numerical substitution. So numerical applications, it will mean that the A equals to 1 times 40 times 20.58 divided by 3.375 times 9. So what do you get for the A? I get here, check 20. What do you get? Okay, 27.1. Okay, it's just 1, okay, pounds. So basically, what does that mean? So case A was this one over here, where we connected this way. And my sketches are not good, but if we build it this way, this would be the maximum load we can apply, maximum shear force we can apply to that cross section, no? If we build it by putting a nail on top. Let's see if it would be any different now if we do case B. Case B, again, would be, so this time we need to be very careful. So this time, case B is what? I think it's the one we have is longer over here. And now we put on each side. Okay, obviously I'm not doing this to scale at all. Okay, so now comes the problem for this one. It was a bit more difficult to determine. So in other words, what I'm trying to say here is that in this case, what would be Q sub B? But we know the V will be, so I doesn't change, no? The spacing doesn't change. What will be the Q? So what would it be? So what are the choices you have? This, no? Or then you can just choose this one or this one. But what I'm trying to say, what are you trying to attach over here? What is the stuff when you think about it? That's why I'm trying to give the idea of what are you trying to attach over here? What is the main structure you're trying to attach? Okay, good. So the main structure we try to attach is this one over here to these two pieces. Okay. So then in this case, this will be our sub B. Basically, what we're trying to do is attach. I know it depends the way you look at it, but we're trying to attach this one to these two pieces, no? Okay. So now the Q again will be what? What should be Q sub B? If I have space to do it here, will be what? So that height over here would be actually what? Again, should be H, no? H is only this part over here, no? H plus the flange times what? Times the web. And what will be the middle of that cross section here? So this is area. And what will be the Y bar? Either H plus TF divided by 2, no? So what would that give us? Oh, okay. Okay, let's do this and then we go back. Go back and forth. So what is H? H was 4 plus, what is TF? A half, no? What's 4 the way up? Hold on 1 second. It's H divided by 2. Because both needs to be the same height. The whole thing needs to be the same height. So this one we had H was this one over here, no? So this one is H over 2? Yes, sir. Oh yeah, okay. So H over 2, correct. So that will be then 2 plus okay, so will be 2.5 times the web was 1/2, no? But wait, it's half of this. I know you are doing the area. Okay, 2.5 times T web times 1, okay, times, so this will be, it should be then H divided by 2 divided by 2, no? Oh. Yeah, but it's H divided by 2. Okay, H divided by 2 plus TF divided by 2. So it will give you what? 4 plus, this was 1/2, no? So 4.5 divided by 2, so 2.25. So if you do this calculation, what do you get? How much? 5.625 inch cube.
H over 2 plus N over 2.
That this one over here. That's what I was saying. This should be H over
2 plus N over 2.
Yeah, that's the same thing.
It's all over 2.
Yeah, everything's over 2 here. It's like if you factor out by 2. So it's 5.625. Okay, but in this case, how many connectors we have? We have 2. So if we go back to the equation, so as before, now we could derive the equation VB will be equal to what? N times VC times I divided by Q sub B times S, where we know in this case N equal to 2, I is unchanged, 20.58, VC is 40, S is 9, Q sub B is 5.625. So what do we get over here? VB will be equal to 2 times 40 times 20.58 divided by 5.625. 9. So what are you getting for VB? 32.52 pounds. So basically meaning that if you build it this way, I know my figures are horrible, but so what should be the conclusion? Which one would resist a higher shear load? A or case B? Case B, okay, but then becomes really, is it cheaper, not cheaper? I have no idea, but you would be using more nails, no? Okay, so it depends on your designs, no? Okay. Okay, so let's do another example that we're going to make up. So you're going to have to help me with the data, just like I said. So let's say new example. And I think this one is the one I mentioned initially. So, okay. So if you want, I kind of give you what could be an example problem. Okay. So let's say you have this beam over here. Maybe we can do it. Let's say here, this is, let's say this will be what, 10 meters. And let's say this will be 50 newtons. Okay. So on this, we have an I-beam. So let's make, is it dimensions? I don't know.
I don't think you started the recording that. Yeah. Very.
I think recording, when it's not recording, there's like a white green frame all around on my side. No, but thank you. I mean, Thank you for double checking because then it's useless. Everything we are doing is not recorded. So, okay, so let's do this. Easy dimensions. I don't know. So let's say this is BF. The web. So you give me the dimensions. What do you want for BF? Give easy values. 5 meters. But it will work, but it's not be realistic, no? Then we make this one 100 meters if you want, no? But, all right, let's put this one 100 meters if you want. Okay, and we can do BF equal to 5 if you want. Then what do you want for TF? 1 meter, okay. All right, we make it up, so it doesn't matter. The H, I'll make it 1. We make it easy. 3, okay, 3, it's fine, 3. Why not? And T web, 19. No, let's make it 1 as well, okay? Let's make it everything. I mean, it's just for the, you're going to be doing the calculation. Let's say 1, 1, 1, all right? Is that possible or not?
No, 19 would.
No, yeah, would be impossible. Okay, so all right, so let's say this. So a plate of, let's say, 0.1 meter. It's to be attached top of the I-beam or the beam of the I-beam. Let's put it this way. By bolts. Oh, no, this one is the blue one. Okay. By bolts. I-beam, let's say VC, whatever. 10 newtons. Point. Determine the spacing S between the bolts. Have everything we need? Yeah. Oh, that's another thing. So that's something we need to design on top. That's good. Good question. So we'll do that later on, okay? But let's first do our equation. So let's see. Let's look at the equations again, and then we work a bit backwards. So the equations we have is tau equals VQ over IT. Q equals to tau times T. And the other one we just derive, which one is I put the spacing, no? Spacing is equal to what? N BC over Q, no? So they are the equations. So in this case, what we're trying to solve for S, no? So let's see what will be the equation. Let's see what we need. So let's say, so VC is given, and we can find out. So Q, the one is pretty easy. So that means that what? So we'll have S equal to N BC. What should be Q? Should be VQ over IT times T, which will give that the equation we need is N BC divided by VQ over I. Okay, so again, I'm making up the problem. So you all have very good questions. So first question he was asking, how many connectors do you need minimum? So let's say we're gonna do this over here. We're gonna put the plate over here. Well, you're gonna add one plate over here, which is how thick we said that one was gonna be. For 1 meter. So how you wanted to connect it? Make your design. 1 bolt, 2 bolts, one very long bolt in the middle. I mean, it's fine, but you see, you have different options. You could put one here, or one long over here, no? Yeah, you have different options. So that would be your design. So your design that you're selecting is to put one over here. Actually, put it 45 angles. Yeah, maybe. Maybe when you do nail on the stuff, what do you put it at 45 instead of straight? What's your question? So basically what happened is that wells, they also have, these books that give you, for example, the same thing we have here, like the V connector is, we selected to be 10. You have experiment that tell you what is the resistance of the well. Does that make sense? Depends how many you can have point ones. You see what I mean? Yeah. So okay. So maybe you decide to do one. But what I was saying, if you work with wood, sometimes if you're gonna do something, you don't put it straight, you put it at an angle. Why? I think you answered the question. Because when you put, what is the difference between a nail and a screw? So basically, if you do this way, but the nail, you can pull it out, no? Those screws are a lot harder, okay? But if you put the nail instead of straight at an angle, then what happens? It's gonna have it all harder to pull it out, no? So, I mean, I don't know if you do woodwork, but sometimes woodwork, when you do trim, you don't go straight, you try to do at an angle, because that way you cannot pull them out, no? Anyway, not everything is engineer, no? It's practical stuff. So anyway, so in this case, since you decided this, let's say this would be, our next would be here S, but for this case, then what we have, N equal to 1, no? Yep. VC, we say is given to 10. All right, what will be V? Now that you're experts in shear diagrams, what would be the shear diagram of this one? All right, it will be a straight line of 50. Shear force will be the same. Okay, I'm not going to go into the details, no? That's why you have the first assignment. So it will be this will be 50. So let's say 1 newtons, 50 newtons. Now, what would be the Q? Q is what we're trying to connect, no? So it's the Q of the plate. So what will be the Q of the plate? Will be what? It will be the BF, no? That we call times 0.1. But you need to do everything. Maybe I'm trying to do too much over here on that little figure. Times what? So will be times H over 2, you're correct. Plus, plus the flange. Plus, maybe I call this one 0.1 over 2, no? Yeah. So can you do the calculation for me? And I'm gonna write down the same thing to do the I over here. 1.275. Okay. It should be this cube. Okay, and now here be careful because this is an approximation. We're going to be very detailed. You need to do the other one, but we can say I will just be the I of the cross section, no? We don't put the one of the plate on top, no? Yeah. Okay, that way it would be easier. So let's do as before. So this will be equal to what? 112 over, we do as before. So BF times what? H plus 2 times TF cube. This time I'm going to do it right, minus 2 times 112 of H minus T of H, no? H should, yeah, the base, sorry, the base. I want to look at the base first. So what? So will be a BF. So BF divided by 2, no? Minus T web divided by 2. Sorry, guys, I know I'm not being too clear here. So BF divided by 2 minus T web divided by 2. That's the base, that's that distance over here. Times H cube, no? Can you please give me that value and double check the one at the top? So now the interesting part is going to be to see if our design makes sense, because we get S equal to too big, no, or too small. We find out, okay? It is what it is. So I think it's going to be very large, my impression. What do we get for I? Can somebody double check as well, please? Somebody get 43 something? Okay, we take the 43. Did you get the 43 over there? Okay, 43.08. Okay, so finally, you can just say, so I'm going to rewrite the equation. So substituting into S equal to N BC divided by DQ over I. So we can say this is equal to N BC times I divided by DQ. What do we get for S? Nothing too crazy. All right, let's do what do we have? N. So 1 times, we said, times 10 times 43.08 divided by 50.
That's 6.76 meters.
Okay, that's not bad. 50 times Q 1 point. So S equals 6.75. Okay, 76 meters. All right, so let's say, or maybe we can just do for safety. I mean, this is the result, but let's say what we can say. If you need to do it, we can put it what? You can make it a bit shorter, like every point 6.5 meters if you want. Because if you do 6.76 of the time might be, I mean, you can do 6.76, no? You want to save some more. But at the end, the design kind of makes sense, no? What is one problem you might have if you have too much information for the top plate? What might happen to it? It might, I mean, that's not something you should know, but it might happen what? It might warp, no? Since, I mean, if it's just a little bit, it's fine, but if you do it too much, it's going to try to warp or something, no? Okay. Okay, so I'm going to stop over here, but basically now, up to today's lecture is whatever is the material will be for the first exam. So you can imagine what can be the first one of the two problems you might have on the exam, no? A beam with some type of loading, with some type of cross section, find the shear bending moment. I can ask you to find the maximum bending, find the maximum shear, and maybe put some type of plates on top, no? And find either the spacing or whatever. What should be the minimum shear force of the connector or whatever? Yes. No, I'll provide the equations. I will probably provide that. I'm probably going to provide an assignment before the exam on this. And then right after that, you will have the exam, okay? Let's talk about it on Tuesday, okay? Yes.
You open this.